Yes.
Okay, so let's start. So this is the tutorial on neuro-symbolic modeling for NLP. I'm Dan Roth, and we're going to give a tutorial together with Maria Pacheco, Shin Wallach, Yejin Choi, Vivek Skrikumar, and then Gold Russell. So let me jump right in, stating the obvious, which is that AI is in the news, largely due to the success of deep learning. And all of you, I'm sure, have been exposed too much to a media that claims that we're almost done, we solved almost all the problems, we are as good as human, and maybe sometimes even better. And hopefully people that work in this domain can qualify these statements and think about the extent to which they are true or mostly wrong. But one thing that I want to attend to that is more relevant from the perspective of this tutorial is that these claims also sometimes say that eventually we're going to train only one big model that will be able to do everything. And this is one of the issues that in many respects we are going to address in this tutorial. And I'm going to start it with presenting a puzzle that just something about the way I think about these issues. I can't see anyone, so I don't know. I'm not going to be able to get answers from you, but hopefully you'll be able to think about it for a few seconds and try to understand what's written in this. So now that you guessed, I'm going to tell you that this says to meet you. And I'm sure many of you already got it, even people that haven't seen it before. And it's really quite amazing how quickly people manage to read these slides, especially if you think about what does it take to do it. Really, you have to be able to identify units that appear on this slide. There are multiple types of units, representation, different interpretations. There are pictures, there's text, there's a layout that is important, the phonetics is important, and each component has multiple interpretation in isolation, but when you put it on one slide, with the fact that I told you that there is a puzzle, so there is a solution, and so you have some expectations here, you can rather quickly determine what is the best interpretation of this slide. The problem here is that of assigning values to multiple variables while accounting for the interdependencies among variables. And this is really the way I think about a lot of processes in natural language understanding. These decisions are often global decisions that require us to be able to make a lot of local predictions driven by different models, trained in different ways at different conditions, different scenarios. And it also requires the ability to put these predictions together in a way subject to some knowledge that guides these decisions so that they satisfy expectations. So of course, our programs need to do a lot more in order to understand and communicate in natural language, but this exemplifies some of the important aspects. The fact that what we did here is really discrete reasoning, and that under the context of this slide, then find the best interpretation of collections. Train for this. I see that the internet connection is unstable, so hopefully you can see me and hear me. Is it okay? Can you hear me well?
We can hear you.
Okay. Please say something if you stop hearing me because I can't see messages. Okay, so let me move on and ask you another question. Here's the question. In Yokneam, in what month of the year is the longest day? Now, I bet that the vast majority of you have no clue what the answer is. However, all of you, I assume, have a plan for how to figure out the answer. And the plan involves figuring out where is Yokneam. In fact, you don't really need to know exactly where it is. You need to know whether it's in the northern hemisphere or the southern hemisphere. And once you know this, because you do have some theory underlying this plan, you will have a solution. Now, of course, this may not be the case if I ask you what happens in New York State with respect to this question, because the answer is written many, many times on the web. But still, the theory that you have that allowed you to develop a plan makes it such that you're not surprised if the answer to Boston is exactly the same thing as New York, and not even surprised if I ask you about Melbourne and you realize that the answer is different. However, what's important here to think about is that you did have to come up with a plan, and how do you express this plan? Or how do you train for this kind of plan and use this kind of plan? So basically, the argument I'd like to suggest in this introduction is that making decisions that depend on natural language understanding really requires reasoning ability. This reasoning ability depends on multiple interdependent models or components, and sometimes it's useful to think northern hemisphere, in my previous example, is a symbol that we manipulate in order to make decisions with respect to when it is relevant. So a single model, not can we train directly to accomplish it. We really have to think about a process, a planning process that determines what modules, what components are relevant, what knowledge is to be accessed to support the decisions and how to do it. So really, this process has to do with exploiting compositionality, which basically means identifying the variables, the components, putting things together according to what you want to do, and of course, supervise accordingly. Let me give you a few other examples. So I can ask the following question to my agent, be it Alexa, Siri, or your favorite one. Will we keep the movie? It's another simple question, but you need to provide the agent with some information. What is the time now? When is the start of the movie? And then maybe you can just go to Google Maps and figure out how you're going to make it. Of course, you can make it a little bit more. We make it to dinner before the movie. The underlying reasoning problem is really the same. You want to think about the time now and the start of the movie. But now you have to incorporate also the duration of dinner. And it's important because this will tell you whether you will make it to a fancy Japanese dinner or maybe just a fast food dinner. And there could be also some implicit hidden events here. If you're planning to drive, what about parking? Maybe parking takes a different amount of time depending on where you're going to have dinner. So I can make this problem as in all these cases, the underlying reasoning problem is the same. You want I can hear someone speaking.
We can either build or lose the trust in certain predictions of the model. We can better compare between different models.
Someone needs to mute themselves.
Models we can more confidently say which one is better. We can identify areas that our model is not.
Excuse me.
Hello.
For example, in active learning, we want to identify which inputs the model is not.
Are you able to mute everyone?
I can't mute anybody. There we go.
Okay. Okay. So thanks. So basically, in all these examples, my point has been that the underlying reasoning problem is the same. We want to know whether the end time of an event, the game, the dinner, is before the start time of another event, the movie. And basically, there's one sort of equation that drives everything here. And this is the fact that the end time of an event is the start time plus the duration. But in order to be able to reason about it or make these plans, you need to be able to identify these compositional components or symbols or variables. And only then you can facilitate training and you can facilitate the learning process. I'm going to give one final dinner example. I know that it's 7 p.m. on the East Coast, so it's time for dinner. So here is another dinner example. And let's assume that you want to talk with your agent, being Siri, Alexa, or your favorite one, about your dinner plan. Let's talk about dinner. The agent would say, where do you want to go? I really enjoy Mexican food, but not when it's spicy. The agent would say, how about Mexican restaurant with plenty of non-spicy options? Yep, is there one in Philadelphia? Here are a couple of good options. So what is really happening here? Any way you want to think about it, a level of abstraction of this decision that the agent is making is it thinks about the existence of a restaurant, of Mexican cuisine in the city of Philadelphia, and this selection has to satisfy some constraints. The restaurants would have to have menus. The menus would have to contain dishes, and they have to exist at least one dish that is non-spicy. Now, of course, the word in my conversation, so all these are going to be really output of models or embeddings, if you want. All the predicates and the functions and the relations here are going to be learned constantly. This abstraction shows, along with some declarative constraints, and reason about it. So again, I see that I get a message that the internet is unstable. I'm hoping that everything is okay. Otherwise, someone will tell you something. Moving on, so all the examples that I've given here serve one purpose. I want to motivate the need for us to think also about symbolic reasoning. So I know that some people in the community today think that symbols are an evil invention of all the AI people, but it's not. Language is really a symbolic system, and any way you want to think about it, look at any piece of text, you'll see that it contains symbols, and we have to reason about these symbols. So even though we communicate via speech, gestures, writing, which are continuous, symbols are the invariance of this communication. And many people have written about it, and I'm putting here a few books that I highly recommend if you want to see what other people that are not computer scientists thought about this. And specifically, I'm going to point to Sol Kripke's book on that said, among many other things, that naming things is key to communication and cognition. So basically, this tutorial is going to put these ideas into some computational framework of how to put things together, how to think about reasoning, where the components are learned models, or if you want, symbols. And of course, this is something that people have thought about it for many years. And I'm showing here a relatively early way in which we've thought about these issues. In this case, I'm showing it in the context of reasoning about time and events. So it was clear that we have to be able to learn models for various components of the decisions that we care about. But at the same time, we have to be able to entertain hard constraints. For example, if event A happens before event B and B happens before C, our decisions have to satisfy that A happens before C. And we also have to entertain soft constraints that sometimes give us some prior of event A, if some events tend to happen before another event. So one of the early computational framework that we suggested to study these things is this ILP framework, where the idea was that you represent variables that are really output of learned models, along with statistical soft constraints and hard constraints, and you have an objective that tries to maximize the score of your learner subject to these hard constraints and soft constraints. Now, this framework doesn't care how you learn the models. It could be neural models, it could be other models. And the framework itself is quite expressive and allows you to think about various kinds of reasoning patterns. Nevertheless, today we can do even more than that. Still, if we want to think about events and relations, what we're going to do is we are going to learn various models for these relations, but we can enforce constraints, logical constraints, temporal constraints, symmetric constraints, other before, but also by, for example, in converting declarative constraints into differentiable learning objectives. If we want, for example, to think about the example that I gave before of n time equals start time and duration plus duration, and it so happened, which is really the case, that it's much easier to identify start time in text than end time, then you can put together a differentiable circuits that allows you to improve your performance on end time, given that you know this relation. So in this tutorial, we are going to address these kind of problems from multiple perspectives. And I'm just going to give a quick survey of what's going to happen. So in the first part of the tutorial, Sean and Yejin are going to talk about integrating symbolic modules, constraints, and knowledge into neural language models. And they're going to talk about modularity, how to use discrete logical constraints, then how to incorporate knowledge into these models. In the second part, Vivek is going to talk about augmenting network architectures and loss functions using logic rules. Really, he thinks about tasks, natural language processing tasks, as contracts that our models have to satisfy, and he will provide various ways how to actually force or allow these models to satisfy these constraints. And finally, Maria and Dan are going to talk about a framework that allows us to think about using these kind of tools on more abstract events, not only, if you want, simple variables, but variables that really correspond to stance of people, frames of mind. If you want to think about what happens to you when you're reasoning about what you read in the newspapers, and they'll show how to incorporate these kind of ideas into this abstract framework. So this is the outline of the tutorial. I'm done with my introduction. In the next part, we're going to hear about framework 1 from Sean and Yejin after a break. And framework 2 and 3 are going to follow. And after the second break, we're going to discuss a little bit challenges and opportunities and see a demo at the end of this. So I'm going to stop here and give the stage to Sean.
Okay, thanks. Can everyone hear me? Just to double check.
Yeah.
Okay. Yeah, so hi, I'm Sean Wellick. I'm a postdoc at the University of Washington and also AI2. And today, Yejin and I are both going to talk about integrating symbolic modules, constraints, and knowledge into these really large-scale neural language models. So a key trend in NLP recently has been the growth of these pre-trained language models, and continuing up to today's day where the models have hundreds of billions of parameters. And the kind of surprising thing is that these models are trained in a very simple way. So we take a vast corpus of text, like most of the text on the internet, and we essentially train the model to predict the next token across all of this text. And the amazing thing is that the language modeling performance, when you do this, kind of improves smoothly as we increase the amount of compute that we spend on training. And in doing so, this has kind of opened up some surprising capabilities, because these language models can both accept a really flexible form of input, so pretty much like arbitrary text, and they can also generate flexible forms of output. And so one possibility is that these language models will start powering, real world applications. So things like question answering, dialogue, and even code generation. But the thing is that when we start to use these models and study them a bit closer, there's still really some key limitations that start to appear. So here's a quote from a paper which trained models up to 250 billion parameters. And they kind of identified a trend here that these models really start to struggle with things that involve deeper forms of reasoning. So be it common sense reasoning, logical reasoning, or mathematical reasoning. And the authors of this paper even suspected that scale alone might not lead to all the performance breakthroughs that we need. So what do these things look like? Well, it might involve things like this, where you get a kind of convincing looking claim from the model, but then later on the model kind of contradicts itself. So somehow it has some inconsistent use of the world knowledge that it has. Other times we can again get kind of sophisticated looking reasoning. So on the left-hand side, here the model actually gets this mathematical word problem correct. But then the model is surprisingly brittle. So if you say step by step versus step dash by dash step, the model's output completely changes and it actually gives you the wrong answer. And then for really sophisticated tasks that are maybe outside of the normal domain of web text, it's unclear whether this paradigm will even be sufficient at all. So these authors of this benchmark, which was published in NeurIPS, basically showed that with these internet-trained language models, the scaling curve on this sophisticated mathematical reasoning task was essentially flat. So aside from reasoning, when we actually use these models, we often want to control their outputs. So for instance, we want their text to be non-toxic. And this might not always be that easy if we train the model to reproduce text that's on the internet. Similarly, we might have some hard constraints that we want satisfied on the output. And so while these models might produce something that looks fluent, here, for instance, the model just ignored two of the constraints that we wanted to include all these words into the sentence. And so today I'm going to talk about three different kind of high-level approaches as well as specific case studies that address these problems. So first I'll talk about modularity, where we move from having a single monolithic system to more decomposed system of modules. And so these can be either neural or symbolic or a mixture of both. Then I'll talk about an approach to using discrete constraints that are specified as a logical formula for gaining some level of control over these models. And then finally, Yejin will talk about how to imbue these models with more knowledge of the world. And in particular, how we can move from the kind of former approach of handcrafting knowledge for the models to actually generating and distilling knowledge from the models themselves. So let me move to the first point. So conventionally, as we saw before, we generate from a single monolithic language model. And a really exciting trend that's been happening recently is that we could actually think about generating differently with actually multiple composed modules. And these can be both neural and symbolic. And I'll give some examples. But before that, what do we hope to get from doing this? Well, we'll see in the examples that this can actually expand the capability of the single model itself. So for instance, some functionality like multiplying two numbers might actually be really difficult for these models to learn, but pretty trivial for something like a calculator. Similarly, like looking up a fact might be easy for an internet search API, but difficult to learn by just training on how these language models are trained. Secondly, we'll see some examples where this gives stronger generalization. And the intuition is that the language model might produce some good outputs, but as we saw before, there's kind of noisy ones nearby. And so we can use some symbolic layer on top of it to kind of reduce the noise from this underlying language model. So as a single formalism for thinking about this, I'm going to talk through a very recent formalism that's come up called language model cascades. And it's fairly simple. And the idea is essentially that we can treat the language model as a single module and then form a cascade of multiple modules. And they kind of interact, all the modules are going to interact through text. And so what is a module? It's just going to be a string valued random variable. And then when we say interact, we really just mean conditioning or observing a value of a particular random variable. So what's an example of this? Well, if we look at a just plain language model, we can give it some question and ask for a distribution over answers, and then sample an answer or use beam search on the model. And going back to graphical models, of course, we can view this as a graphical model where we have a question variable that's been observed, such as this math word problem here. And then the parameterized model gives us a distribution over answers. And in this case, when we sample an answer, it ends up getting it incorrect. Now, I'm not going to go into too much detail on this part of it, but you can equivalently view these graphical models in terms of what's called the probabilistic program. And the probabilistic program not only has normal variables, but actually has random variables within its execution. And so one way you could think about these systems that we're going to talk about is that we're actually creating more and more complex probabilistic programs. And now the language model is almost just like one line of code within that program. So what's an example of what I'm talking about? Of course, you can provide a prompt to the language model and just add it to your graphical model. But a really common trend that's been appearing recently is actually splitting prediction into two parts. So now we produce some intermediate rationale before we produce an answer. So in the case of math word problems, instead of directly answering a question, we might ask the network to produce this intermediate rationale, and it kind of intuitively gives the model a chance to decompose the problem into multiple parts. And this can be formalized as just another variable in our cascade, and then we marginalize over that variable to get our original distribution over answers. Now, in practice, we do something pretty simple, which is just approximate this distribution by just sampling one rationale from the model and then sampling an answer. We can use the same formalism to kind of write down how we can integrate a symbolic tool into the cascade. So here, now we can think about the model generating part of its rationale and then stopping when it gets to a calculation. So like 30 times 40. And now instead of having the language model output the answer, we can actually call some external calculator or some symbolic system. And so now this kind of offloads the need to learn how to do multiplication. And we kind of use the language model for what it's good at, which is maybe this like higher level generation of the solution structure. So this idea actually came up in this paper in 2017, which is shown below, Program Induction by Rationale Generation. But we've kind of seen this appear more recently again with these really large-scale language models. So this paper from OpenAI in 2021 developed this math word problem data set that has these intermediate rationales, as well as these calculator annotations shown in red. And so if you use one of these large language models to directly predict the answer, it does fairly poorly. And then using this rationale along with the answer, along with the calculator, leads to a big jump in performance. Then we could think about actually adding some additional module onto the cascade, which is a learned verifier. So here you have another model which learns to predict the probability that a given rationale and answer is correct. And the benefit is that now we can apply this, this model multiple times and just select the answer that's ranked the highest. And you can see that this again leads to a huge jump in performance versus originally just using this language model on its own. And then another aspect to this modularity is that you can vary the size of the different components. So here the size of the verifier is kept held constant, and then we just increase the size of the generator, and you can see that we get another huge jump in performance. So this idea has come up in other settings. So for instance, instead of a calculator, you could imagine calling out to a search module or a retrieval module. And again, the idea is fairly simple. It's that you just have the language model generate some query to the symbolic system, and then you append the result into its context. And so in this case, with this retrieval module, this paper demonstrated that you can kind of use you can get much higher performance from much smaller models. So in orange is the one without the external module, and in blue is the one with. You could take this calculator analogy to the next step and say, instead of outputting text, which we kind of can't execute or check, we can instead frame these math word problems as producing just a standard Python program and then executing it to get some answer. So recently we put together a benchmark which kind of unifies 20 different math tasks in this form, and it'll appear soon at NLP. And so the idea is now the language model can use tools like NumPy or SymPy and use variables to keep track of state in the problem. And so it kind of has this separation of concerns again, of the execution or what's already capable from a tool and what the language model might be good at. And again, when you do this separation, on the left here, you can see the numbers that you get by just predicting the answer. And on the right is what we get when we predict an executable program. And so this helps both in terms of in-domain generalization as well as out-of-domain generalization to new tasks. So now we'll go through a case study of trying to use these ideas for solving these very sophisticated problems that are typically out of reach for these types of systems, like the type of mathematics that we'd see in an International Math Olympiad contest, for example. So one approach to going about solving a problem like this is to kind of, just treat it as a language modeling problem. So we could imagine just passing this problem to our neural network, scaling it up to say 500 billion parameters, and then trying to predict the solution. And surprisingly, there's been some recent work that demonstrates this is possible. But what you run into is that despite the flexibility of this approach of just generating arbitrary text, with these sophisticated problems, it gets very, very difficult to actually tell what's correct and what's incorrect. And so in particular, kind of no matter how good the system is, it's not grounded in anything. And so we have to ask a human to verify whether it's correct. So an alternative is to work in the space called formalized mathematics. And so here, a theorem and a proof or a problem like this looks more like source code. And there's been several systems or interactive theorem provers that have been developed that can essentially process this and then verify whether it is correct or incorrect. And so now we kind of get the other side of the coin, where we're able to verify some mathematical statement or its proof, and it's kind of grounded in this computational system. But on the other hand, certainly like this program here on the right is much less flexible than the language or the mathematical language that you see on the left. And this still requires some domain-specific expertise. So the amount of training data that we have is relatively limited. So the question is like, can we use some modular system to get the best of both worlds? So we recently looked into this and developed this approach called draft, sketch, and prove. And so the idea is we're going to start in the space of natural mathematical language and use a very powerful language model. This one, it's called Minerva, to produce some informal proof. And so now the difference is, instead of considering this as the final output, we're just going to consider it as a draft. Then we're going to have a separate language model that translates this into a sketch. So a sketch basically contains the high-level reasoning steps in one of these formal programs, but then it kind of leaves out the details. So it leaves out the proofs of these intermediate steps. Then the third step of the chain is to pass this sketch to a symbolic off-the-shelf prover. And you could think of these as being very good at kind of proving these smaller intermediate conjectures, but they're bad at like proving the whole thing from scratch. And again, we can sample we can sample this chain many times until we find one that is verifiably correct at the end. And so what we've done here is set up a nice division between neural and symbolic, where we use these powerful neural language models, in this case, just through few-shot prompting, to generate these informal proofs and the high-level reasoning sketches. But then we use the symbolic tools for what they're very good at, which is this lower-level closing of the gaps. And so together, they're able to lead to some pretty surprising results. So here's an example on a question from the International Math Olympiad, where, again, this neural system is fairly sophisticated and can output some informal proof. Then we turn it into some high-level sketch, and then close the gaps with the symbolic prover. And so you can see on like the second to last one, that what the symbolic prover outputs is, I mean, this probably never appears in this language model's training corpus. So it's kind of a nice separation of what each system is good at. So if you use the symbolic prover on its own, again, doesn't do very well. If you try to predict the proof just end to end without the symbolic prover, again, doesn't do as well as the previous state of the art. But then either using a human written informal proof or one that we saw before generated by a language model, we're actually able to exceed the state of the art on these math competition, benchmark. And so as I mentioned before, another nice thing is that you could just like keep sampling more and more. And you could think of this as being some inference time algorithm. So it's some algorithm that you apply at inference time, and it's fairly simple. It basically just says, you know, sample many solutions and pick one if it's correct. But in a completely different domain, we could think about incorporating symbolic tools into more sophisticated inference time algorithms. So here's an example, and I won't go through all the details due to time, but the basic idea here is that you want the model to just give you a true or false assignment to some common sense question. So such as like war cannot have a tie. And the idea behind this inference method is that you have the language model enumerate this tree of explanations. And now the tree is going to inherently be contradictory in the sense that, like, you ask the language model to generate a true position. So here it says, like, wars always have a victor and a loser, as well as a false position. And you kind of keep enumerating the tree. Then you can score this tree and actually frame this as a maximum satisfiability problem, where you want to assign some truth value to each node in the tree, and in particular, assign some value to this node at the top. So here again, we have this decomposition between the flexible neural network, kind of enumerating this tree, and then the symbolic solver that resolves things at the end. So as we saw, this modularity involves multiple modules interacting through text, and you have this nice separation of concerns, as well as some robust layer on top of a noisy network. Then briefly, let me talk about the second point, which is how do we incorporate constraints into these networks? So again, we saw that these language models are often difficult to control. And again, we can look to the inference or the decoding algorithm to try to enforce constraints on their output. So one form of constraint is called a lexical constraint, which is a word should or should not appear in the generation. And so this is useful in things like table to text or translation, and also in things like theorem proving, where you want to ensure that certain theorems, for instance, are used in some proof. So this method that we developed kind of frames this problem as specifying the constraints through some logical formula in conjunctive normal form, and then using a search procedure that's similar to A-star search to look ahead into the future to see if constraints are satisfied. So the idea here is to basically modify the normal beam search procedure, which goes from left to right and scores tokens without reference to any notion of constraints. And instead incorporate two different scores. So one is going to increase the probability of a token if it matches a constraint. And then the other is going to look ahead into the future and try to estimate whether a constraint will be met. So here, for instance, we'd increase the probability of winter because our look ahead will find that snow is more likely to generate that. And again, just due to time, I'm just kind of giving you a high-level sketch of this, and so be sure to check out the paper if you're interested in. So this can lead to good performance in terms of the constraint decoding, and you can also plug it into off-the-shelf models to enable constraints. So I'll just go over this really briefly due to time, but we did apply this idea of using constraints to this sophisticated theorem proving setting and showed that, again, using a language model on its own was sort of far worse than using one of these constraint decoding algorithms to actually come up with a correct proof. So those were the modularity and the constraint parts. And now I'll hand it off to Yejin to talk about knowledge.
Okay, so yet another form of symbolic integration into reasoning is in the form of knowledge that is symbolic. And in particular, although we do rely on language models for a variety of NLP applications today, they're fundamentally not knowledge models. So this symbolic knowledge distillation builds on our two previous work, Atomic and Comet, which are symbolic and neural common sense models. And the atomic was previously fully crowdsourced by humans. And there was a follow-up work, COMET Atomic 2020, that enhances over the previous versions of this atomic as well as COMET. Let me show you summarize the viewpoint about Atomic 2020. So given a center event like X gets X's car repaired, there's a variety of common sense reasoning that comes to our mind. For example, as a result, you might need to pay the bill or call Uber or Kakao for a ride. And in order for that to happen, you need, this is precondition, you need a mechanic or money. We can also think about object-centric knowledge, such as the fact that money can be used for paying repairs, or that money is often made of paper, which, by the way, the paper bills can be folded into origami if you really want to do that. So there's something about stereotypical use cases as well as affordances of different physical objects. So we have a bunch of these relational common sense knowledge hand annotated as of 2020 that amounts to 1.3 million if-then rows over 23 different inference types or relation types. And that was all fully annotated up until 2 years ago. So why would this be useful is that it allows us to teach neural common sense models built on top of off-the-shelf language models such as BART, or you can use GPT-2 as well, which will perform much better than GPT-3, which is too large even to fit into the slide. So GPT-3 is almost 400 larger than this BART version of COMET. And in terms of the accuracy of the prediction, COMET is significantly better than GPT-3, which is about 73% good. That's a remarkable improvement over how GPT-2 used to be. So there's something quite interesting about how much scale alone can give us in terms of common sense knowledge acquisition. But it's just still far off from 100%, and it's still much worse than the smaller model, COMET. So since our development of Atomic and COMET, or some combination of both, very creative people all around the world demonstrated a variety of different and surprising use cases out of either of these common sense models. So given that, it seems that we do want to improve this further, which is why we worked on symbolic knowledge distillation. Now, the idea is that we are going to start with this GPT-3, which is too large, but showing promises in common sense capabilities, and then make it smaller but better. And in general, when we think about knowledge distillation, as you make it smaller, you get worse model. But in this case, we can actually make it better because this knowledge distillation funnel is of a particular kind that has critic insight. And then byproduct of it is going to be a symbolic knowledge graph. And then the final model will be smaller but better. So it builds on the original idea by Hinton et al., knowledge distillation, that starts with the teacher model and then train the student model by optimizing this cross entropy between the teacher and the student. And in its original version, the output was a simple classification task, which is easier for this type of computation. But now we're doing a common sense model for which the output space is basically any open text generation, which means the output space now is intractable. But well, that's not a problem in practice in some sense, because everybody does sampling and so we can. And in fact, it turns out by doing this sampling of a particular common sense prediction, the byproduct of it is essentially symbolic knowledge graph that is interpretable by humans. Another interesting thing to note is that the output student model will not be the general language model, but rather common sense model. So it turns out the resulting symbolic knowledge graph, which we named as atomic 10x, can be much bigger compared to the atomic 2020 written by humans. So here, the height of the bar represent the quantity in millions. And so atomic 2020, with respect to a subset of relation types, 7 different subsets that corresponds to causal common sense knowledge, was less than 1 million pairs, whereas atomic 10x can be much bigger. But here you notice that there's a black portion and green portion. Black portion is bad portion, green portion is good. And you might remember that GPT-3 was good about 73% of the time. So there's a lot of this noisy portion. It turns out if we train a small critic model based on simple classifiers such as Roberta, which is not very good, by the way, it's not a good classifier, because if it were a perfect classifier, we would have already solved common sense. So it's not a good classifier. So it throws out a lot of good portion, green portion, but it's capable of reducing the black portion considerably, such that we can actually attain higher accuracy than the original atomic 2020, while it's much bigger in quantity. And it turns out, so this is now performance of different models. GPT-3 was 73%. If we do classical, more vanilla distillation, it turns out the resulting comet on its own is already better than the teacher model to some degree. But it's not as good as the comet trained on human-authored symbolic graph. But finally, when we teach this comet based on the combination of the original GPT-3 together with critic filter, we can attain the highest performance we have seen so far. So this is an exciting result in the sense that now we are entering a new era in which now we have a machine-authored symbolic knowledge graph that wins over the human-authored knowledge graph, at least with respect to this causal common sense reasoning that we focused on in all criteria, scale, accuracy, and diversity. So I think I'm running out of the time, so I'll stop here. And I think we're now having a break, maybe 10-minute break. I don't know.
Yeah, I think 10-minute break will do.
Yeah.
During the break, if anyone has any questions, also feel free to jump in.
So we'll start again at 8:05 East Coast time, I guess.
Yeah, I think that's 9:05 Korea time.
Okay.
Yeah, Korea is even more east than East Coast.
Yeah, I liked the references to dinner in the introduction. I was actually baking a pie before this. It was 4 p.m. here. Pumpkin pie.
Shall we get started, maybe?
Yeah, it's time.
Yeah. Okay. I hope you can see the right screen. I can't see any of you or any chat. So if there are questions or anything, maybe you can just unmute yourself or say something. All right. So I want to talk about some some ideas around how to use logic and symbolic rules to change neural network architectures or design loss functions so that the network likes to satisfy the rules. To get started, I want to talk about, I'm going to frame a lot of NLP tasks, especially tasks that involve assigning categories to things, as contracts. What I mean by that is we may have a data set that might tell us something about a task, but really when we think about the task, or when we have a model, we may want the model to do more than what the data says. Then I'll talk about how we should think about it, this problem as trying to learn from knowledge rather than from examples, and in particular, discuss an idea of how we can relax logic into differentiable units, differentiable functions, and use them. And then I'll present a few places, a few tasks, few case studies where this idea has been applied. So let's get started with how tasks are contracts. I'll start with this example of natural language inference. This is one of the running examples through this section. If you've not seen this task before, you're given a premise, like this sentence here: before it moved to Chicago, the aerospace manufacturer Boeing was the largest city in Seattle. And you're given a hypothesis. You can read it yourself. And you're asked whether a reasonable person would read the premise and the hypothesis and decide whether the hypothesis is true, it's entailed, or is it false, it's contradicted, or it's unrelated. In this case, if you give this to a model, actually this is a few years old now, but most reasonable models would say that the premise entails the hypothesis. It's quite likely that the premise entails the hypothesis. So this suggests that the model is doing something intelligent. So now let's kind of expand on how a user of such a model might want to do something with this. Suppose the user might take three sentences, like here: P, H, and Z. Given P, the hypothesis H is entailed, and let's say the model predicts that. Given H, given that John is traveling to Berlin, we might ask, is John having lunch in Berlin? And it's reasonable to assume that there's a contradiction there because John cannot be traveling to Berlin and having lunch in Berlin at the same time. Now let's suppose that a model makes these two predictions. And then given P and Z, it says there's no relationship between them. Most of us would note that this violates a rule. Because if for any sentence, I don't care whether we know those sentences or not, for any three sentences, P, H, and Z, if P entails H and H contradicts Z, then P should contradict Z. It should not predict that there's no relationship there. And yet, a model that's based on BERT, that at that time was, this was in 2019 or 20, was getting more than 90% on some benchmark, violates the simple rule on almost half of a collection of triples. The question that is of interest here is, given theory, and I'm using the word theory in a loose sense, of this kind, can we guide models to become more reasonable, more correct? To think about how to do that, I want to argue that tasks define predicates. Any task that requires categorization of examples or parts of them, and there are a lot of NLP tasks do that, define predicates that are native to that task. For example, the natural language inference task defines three predicates: entail, contradict, and neutral. And in this case, this one labeled example that P entails H is really giving us information about all three predicates: that P entails H, that P does not contradict H, and P and H are not neutral. Labeled examples show examples of these predicates in action, and the goal of learning is to find models that can find the best fitting predicates for future arguments. That's a very complicated way of saying we want models to predict the right label. But thinking about tasks as defining predicates through their labels allows us to model the behavior of, or define model behavior using constraints. So I can say if P entails H and H entails Z, then P should entail Z. I can write that as a simple rule. Entail PH and entail HZ implies entail PZ, and there are other such transitivity constraints. Similarly, we can write a contract that I don't care what the model is, but the contract predicate should be symmetric. If P is a contradiction of H, then H should be a contradiction of P, if and only if. So I'm thinking of these sorts of expected model behavior that goes beyond what the data set says as a kind of a contract that any user of the model is going to expect. And one goal we should think about when we are training models is, how do we make models that satisfy these contracts? Let's look at a second example. This is an example of the NLP task, semantic role labeling, where we want to predict who did what to whom and such things given natural language text. So if you have this sentence here, we have two events that are happening. There's the eating event and there's the leaving event. For the eating event, we know that the mouse is the eater. In this in a particular formalism of this task, the doer of the event is R0, and the thing that gets that's used up here is R1, and so on. So the thing that's eaten is the cheese. And when did it happen? This is when the farmer left the kitchen. This is the time. There's another event here that's the leaving, and it has its own arguments. The farmer is the doer, the leaver in this case, and the place that's left is the kitchen. That's the label here is R1. Now, these labels are defined by prop bank, and this is a a resource that exists out there. And importantly, prop bank, the definition that defines all these labels, also gives us the contract for semantic role labeling. It looks like this. There's an input, that's a sentence, and the output is a structured collection of semantic frames such that they satisfy certain constraints. And these constraints are symbolic, and they come from the definition of the task. So core arguments cannot repeat. Certain labels should not show up more than once, but certain others are allowed to show up more than once. If certain labels show up, like R0 here, if certain labels like R0 show up, then R0 should already exist. And you don't have to worry about what these things mean, but it's easy to note that these are essentially symbolic constraints that the task is required, that the model is required to satisfy. So I'm calling all of these contracts. These are essentially the expected behavior that any reasonable user of a model will hope the model satisfies. If these labels satisfy these symbolic properties, then we can think of two questions. How do we inject this knowledge into the modeling process, into the prediction process, and when should we do it? And a particular version of this that I'm going to talk about in this section of the tutorial is, can we do this with the existing gradient-based machinery that we all know and love, like say PyTorch or TensorFlow and such things? So to answer this question of how do we use existing gradient-based machinery, I would like to think about generalize the notion of learning from examples, which is what machine learning is usually framed as. From that, I want to go to learning from knowledge, where knowledge can take the form of predicates that define things in the form of constraints, rules, and so on. In general, they're going to be statements in logic. So we'll be looking specifically at how we can relax logic and use relaxed logic for learning. Knowledge or logic can be involved in many different stages in the pipeline. It can be used to influence the design of a model, either automatically or manually. It can be used to influence the design of loss function, again, automatically or manually. It can be used at inference time using some sort of, say, structured inference, like say beam search, if you will, and possibly in all of these places. Specifically in this section, I'm going to talk about how we can automatically guide model design and loss function design using the logic. So to do that, we need to think about these two worlds. There's the neural network land and logic land. Neural networks are units of differentiable compute. They're easy to use because we have fantastic libraries, except they're hard to supervise because we need labeled examples. On the other hand, logic is not differentiable. It's expressive, but it's not differentiable. So somehow our goal is to combine both these worlds. And to do that, we need to answer a few questions. But before that, I just want to restate what our goal is. Our goal is to take statements, expressive, symbolic statements that are easy to state for domain experts and use them with differentiable compute in a flexible way without actually having to worry about how to, about a lot of the low-level details. But to do that, we need to answer three questions. The first one is, whenever we talk about symbolic rules and logic, we do that in the context of predicates. So we need to find the predicates in the neural networks. The second question is we need to find somehow, or the second question is related to this section of the tutorial here, where we are trying to make logic differentiable so that we can use it with the existing machinery. And the third one is, what do we do if we make logic differentiable? So let's go through these one at a time. The first one is about how do we find the predicates in neural networks? And I'd like to claim that all neural networks expose interfaces in the form of certain nodes in the network, in the computation graph, that have external meaning, that have meaning outside of, that are not anonymous, just units of compute. An easy example of that are the labels. Remember that I argued that labels are predicates. So we have the example that we've already seen. John is on a train, John's traveling to Berlin. If a model, here I'm just calling it BERT, you can throw in your favorite and the latest and the greatest model, predicts the label entail. This is equivalent to saying that this model has the belief that this predicate is true, entail of P, H. So labeled examples are predicates. Labeled data sets can be seen as formal specifications. So if I have a data set with 4 examples, P1, H1 being label and P3, H3 being neutral and so on, that's the same as a big conjunction here of these over these predicates. For example, neutral of P3, H3. And these nodes here, every label here corresponds to a particular node in this computation graph. In this case, if you are building a model on top of BERT, for instance, you would have a linear layer with 3 outputs, each of one corresponding to one label. Sometimes there are predicates inside neural networks. So an example here is the somewhat old now model that was defined in 2016 for natural language inference called the decomposable attention model, which would encode the words into vectors for the words of both the premise and the hypothesis, and then try to build a soft alignment between the words using the attention mechanism. And then there's a label that gets predicted based on the attentions. Now, attentions are really soft alignments, but we can reason in terms of alignment. So here, this edge here, if it is true, it corresponds to the fact that the word traveling is aligned to the word train. You might say this is an old model and nobody uses this anymore, and we just use GPT N, whatever is the latest N. But the fact is, even with these models, as Sean pointed out earlier, we try to modularize these models and kind of group them together and chain them along. So now the model itself becomes really large, and there tend to be these nodes in the middle that are differentiable and yet have external meaning. And all of these can be thought of as predicates. These nodes in a computation graph that have externally defined meaning, I'm calling them named neurons. This is a node, a neuron, that I have assigned the name to. And by giving it a name, I can start using it to construct rules. Named neurons could be any node in the network, any output node in the network, It could be inputs to the network. It could be deterministic properties of the inputs that are not explicitly in the network, but can be added. And sometimes, as I just mentioned, internal nodes could also have externally defined behavior. All of these are going to give us our vocabulary, and they are going to be the means for bridging the predicates and the rules with the neural networks. The next question is about making logic differentiable. How do we make logic differentiable? For this, we can think of Boolean operators as functions that go from the discrete input space to a discrete output. So not, for example, can take a number from, say, 0. It can either take a 0 or a 1 and then flip the value. Or and can take two numbers, both either 0 or 1, and produce a value that is 1 if and only if both inputs are true. We can think of, if we think of these as functions, we can also think of relaxations. Turns out that this idea has been in existence for almost 100 years now. And the conceptual tool here is something called a triangular norm, or T norm, which defines systematic relaxations of logic. Some of these T norms are continuous and subdifferentiable. Let's look at an example by focusing on this conjunction. Recall that a conjunction is true if and only if both its inputs are true. In other words, a conjunction takes the value 1 if and only if both inputs are 1. I can plot this in this sort of a plot here with two inputs and 2 outputs. And you see that I can relax, I can fill up the space in between in many different ways. Each way in which I can fill up the space between these in the region that is not defined for the Boolean conjunction, but is defined for the relaxation, each way in which I can fill up the space gives us a different T norm relaxation. Here I have 3 relaxations called the product, Lukasiewicz, and the girdle, and there are an infinite number of them. I'm just going to show you a bunch of equations here. You don't have to try to read them. You can find them up. You can look them up easily. The point is that the inputs and outputs to these relaxations, instead of living in the set 0, 1, live in the entire range 0 to 1. What these relaxations guarantee is that at the boundaries, when the inputs take the value 0 or 1, these relaxations behave exactly like Boolean logic. And in between, they fill up the space as the previous picture showed. The key point that I want to make here is, if we can relax all the 4 Boolean operators, then any Boolean expression, we can convert it into a differentiable function. So that's going to be our answer. The way to make logic differentiable is to just use a T-norm relaxation. The next question is, what can we do with these relaxations? Now, one way or another, when we talk about symbolic rules helping a neural network, it's going to help it by introducing inductive bias. Specifically, we can, in this case, we can introduce inductive bias by changing the network architecture so that the model prefers to satisfy the constraints or is more likely to satisfy the constraints, or by regularizing learning so that during learning, models that violate constraints are penalized more. Let's go through these one at a time, and I'm going to show you some cartoon examples that illustrate how this is done. Let's look at the first one at the beginning. So suppose you have this neural network, and let's say that there are many layers both before and after all these nodes, but there is this layer of A's and a layer of B's. In particular, I have 2 named neurons, meaning that I have these nodes have external meaning, A1 and A2. And there's a neuron here which also has an external meaning, B1, so that I can write this rule. If A1 and A2 are both true, then B1 should be true. Let's look at how this gets injected into that model. Importantly, B1 is not directly connected to A1, A2, A3. There are many layers in between. And B1's previous layer is something called X. And there are some parameters so that B1 is some nonlinearity applied to that, the pre-activation score. So if I take the left-hand side of this rule, A1 and A2, I can convert it into, I can relax it with Lukasiewicz logic to get this extra node called D. I don't have any new parameters here. And if you carefully, this is basically a rectified linear unit. And now I need to connect this D to influence the value of B1. What I need to do is, if the value of D is high, in other words, if the left-hand side is true, then B1 should also become high. I can do that easily by just swapping out this node B1 with a constrained node, I'm calling it B1 prime, that has an extra input. If A1 and A2 are true, then D becomes true. A1 and A2 are close to 1, then D becomes closer to 1. And so we add an extra positive number to the pre-activation score of this node. And so B1, the value of B1 becomes more true. And in this way, the model becomes more likely to satisfy constraints. You can think of this, another way of thinking about this is, even though there are many layers between the A's and the B's in the original network, by constructing this extra path, I can essentially offer a short circuit without adding extra parameters. There's an extra hyperparameter that I've introduced here, rho, which controls how strongly this constraint is enforced. There's another way in which I can use logic to influence neural networks, and that is by by converting the constraints into a regularizer. So to do that, we need to think about data and knowledge as essentially the same thing. Labeled data is a collection of propositions about examples, and I showed that a little while back. Knowledge can also be written as rules. Together, all of these things can be written as a collection of rules of this form. This expression here could be labeled examples, it could be constraints, whatever. Now, our goal is to find a model such that rules of this form are true. We prefer models that set all these rules to be true. Or alternatively, because we are using these relaxed versions of logic, our goal is to find models that make these rules as true as possible. Or in other words, we want to find models that maximize a t-norm relaxation. If you prefer the framework of minimization rather than maximization, you can say that we want to find models that minimize the negative relaxation. And that way we get what are called inconsistency losses. We can now take any neural network model, any neural network library, pick your favorite optimizer, just relax the constraints and write down a loss function and just give it to the model. An interesting side note is that this process, if you apply this to the just labeled examples, suppose you do not have any constraints, you just have labeled examples, and you use a specific relaxation called the product t-norm, we essentially reinvent the cross-entropy loss. But with these additional kinds of constraints and things, we have new kinds of losses that don't really have names. So this is another way to motivate the cross-entropy loss. All right, so I have maybe about 10 minutes. So I'm going to talk about a few case studies. Two of them are going to be about the task of natural language inference, and the third one is going to be about the task of semantic role labeling. The first one is about natural language inference. In this case, I'm going to talk about specifically how the idea of augmenting a network by attaching these extra nodes to short circuit the model, how that process can improve things. This requires named neurons inside the model. So we worked with this decomposable attention model, which is, as I said, a little dated right now, but it's a good case study. We had only two constraints. All of them are written in logic, but I just didn't want to throw any more math on the slide than necessary. I say that, but there's going to be a lot of math very soon. There are only two constraints. The first one is if two words are related according to an external resource, say WordNet or a concept net or something, then they should be aligned. The other constraint is if no content word in the hypothesis is aligned to the premise, then the label couldn't possibly be entailed, because predicting an entailment requires some evidence. And these were converted into the relaxed version. The nodes were added to the decomposable attention model. And a specific question that we were looking for in this case study, and we'll see also in other ones, is how much do these models get influenced as a function of how much data we use. So we have experiments on different amounts of training data. So what we found is, first of all, the constraints actually help the model. Unsurprisingly, or maybe surprisingly, there are larger improvements if the amount of training data is limited. So if there is less training data, then these constraints can actually help the models more. And so this means that these sort of symbolic approaches are more helpful when we do not have too much the luxury of annotated data. If we have a lot of data, then maybe we can just believe the data because these constraints don't seem to help. This was an example of how augmenting the network helps. The second case study involves the problem of inconsistency. So remember, at the beginning of the section, I mentioned that there are two contracts that the NLI task should satisfy. The symmetry constraint says that if a sentence P contradicts a sentence H, then the H should contradict the sentence P. Now, this may seem obvious, but remember that when we give these sentences as inputs to the model, we have to decide on an order. Essentially, this constraint is saying the order doesn't matter for the contradict label, but for the other labels, it does. There are co-transitivity constraints of the form that we saw before, and we can apply the same process where we relax these constraints into loss functions and just train the model with these extra loss terms. Once again, we did these experiments where we control the amount of data that the model is trained on. And there are a couple of interesting points to note. First, in this picture here, I'm showing inconsistency. So lower is better. Inconsistent, basically lower means that the model is less bad in terms of violating these constraints. So the first interesting observation is if we keep adding more and more data, the blue line here is the unconstrained model and the red one is the orange one is the constrained model. If we add more and more data, the unconstrained model does not necessarily seem to improve in terms of its inconsistency. Just adding more data does not seem to make models consistent. We need to actually teach the model to be consistent. And the second point is that adding these sorts of logic-based regularizers makes the model does seem to help with consistency. For example, even with 1% of the training data, adding the regularizer gives us a model that is more consistent than a model that was trained on 100% of the data for this particular loss, for this particular error, symmetry. And same thing for consistency. A model that's trained with 1% of the data with constraints is better than a 100% model without the constraints. All right, our third case study, I see there's a comment. So there's a question that in the chat for the PHC example, it looks like entail. If you can unmute yourself, maybe it'll be easy. Sapan, are you there? I'll just read out the question maybe. In the PHC example, it looks like the entails P1 H1 and the contradict H2 Z2 and contradict H2 Z2. Do we need to specify that H1 equals H2? So there are only 3 examples here because this H is common. And similarly for the entail and the contradict also. It was the H1 equals H2 by construction. So in defining the loss, we just summed over a collection of triples. So it automatically became H1 equals H2 was satisfied by construction. I'm not sure if I got your question, but I hope I answered it nevertheless. So let's now look at the third and the final case study in the task of semantic role labeling. And here I'm going to kind of go into a little bit of gory detail of the, just to show you the constraint, mostly to point out that we can write rather nasty constraints and compile them into loss. So we have this constraint called unique core roles, which in English is rather easy to say. There is a set of arguments, the set of labels called core arguments. And For any verb, it can each core argument label can occur at most once. To kind of make this more into formal into a formal language, we can say for any verb and any word I, any verb you and any word I in the sentence, if the model labels the ith word as the beginning of the label X for some label, that's called a core argument. So X can be one of these 6 things. Then for any other word indexed by J, the model cannot predict that that jth word is the beginning of the core of the same label. Now, this is a rather hairy constraint because it involves some universal quantification over many things and an implication, and there's a lot going on here. But the process is essentially the same. The recipe is we can compile this into a differentiable expression using a t-norm. In practice, we had to use a combination of t-norms because of some stability issues, and the paper has more details. And then we can just minimize the negative of this expression as part of training. In other words, we just add another loss term to the existing loss. There are a couple of other constraints. There's one that's called the exclusive overlapping role, which simply says that if the model predicts that there's an argument there's a label in this span, for some other predicate, for any other predicate, the other span can be entirely contained inside the original thing. It can be entirely outside, but you cannot have a case where there's a partial overlap of labeled spans. And then there's the core role constraint, which says that certain verbs can only take certain labels. And this is defined in this big list of big resource called PropBank. So once again, there are 3 scenarios that I want to consider here. The first one is the low data regime, where we have only a limited amount of data, and we compared models with and without constraints. We started off with a strong Roberta baseline, which at that time was the state of the art. And what we found was constraints improve precision more in the low data regime. Turns out they also improve the F-score, but the precision is the one that sees the biggest improvement. And constraint violations are reduced. An important point to note here is in this setting, at inference time, there are no constraints. At inference time, we are just predicting labels one word at a time. There is literally no computational low burden that is added at inference time. This was a deliberate choice. In practice, it makes perfect sense to add constraints at inference time also, so that we get essentially no violations at the end. The second scenario is, let's say we add more training data. In this case, we worked with the Connell 05 data, which had 90K propositions. And surprisingly, even with more training data, there was an improvement in precision recall and F-score. And especially interesting was the fact that with essentially doing nothing at inference time, we got out of domain improvement because essentially the model satisfies this implicit contract better. The constraint violations were reduced for the core roles and the frame constraints. Once we get more and more data, it does not seem to violate one of the constraints because the data essentially teaches the model that. In the third case, where we have a lot more data, where we have, this must be Connell 12, I think, where we have 250K propositions, turns out the constrained and unconstrained models are essentially comparable. There is like a minor improvement, but I don't believe it makes sense. So once again, we have the same story. If you have a lot of data, it's okay to believe the data. I just presented 3 case studies, but there are other examples where the same idea has helped. Other tasks like question answering, chunking, jointly detecting digits, and also predicting things that, the results of numerical operations, some information extraction type tasks, and so on. The general flavor of the results is essentially the same across all these tasks. When we have less data, or no data even, knowledge gives us better statistical models. We can inject these invariances into learned systems. And surprisingly, these learned systems don't pick up some of these invariants even when there's a lot of data. as a final advertisement, before I wrap up, I want to give a shout out to this library called Pylon, which allows you to learn with these kinds of constraints and other ways to relax constraints also. All right, I think I'm at the end of time, so, or at least my allocated time. So I'll wrap up. If there are any questions, you can shoot them to me now or later. Right, thanks. Is it Maria next?
It's Dan.
All right, can you see my screen?
Yep.
Okay. All right, so hi everyone. I can sort of see the chat, so if you have questions, please write them down. If you feel ignored because I'm not paying attention to the chat, then just unmute yourself and ask. In this part of the tutorial, we'll try to think about ways in which neuro-symbolic NLP can help us deal with problems in computational social science, and specifically study the interactions between language, social group and their dynamics, the kind of group identities that form, the opinions that circulate within those groups, and so on. The key idea would be to try to come up with a set of symbolic explanations over which we can reason about such inputs, things that indicate the reasoning behind opinions, things that identify how people think about the world. And these symbols can be embedded, which would allow us to extract them from linguistic data. In order to make these things a little bit more concrete, let's think about a situation that is pretty common in NLP, where we have physically grounded language. In this case, we have a phrase like close it, which really can only be understood in the context of, there's an open door and you want it closed. So the true interpretation of close it is close the door on the right, and that could really only be obtained by having access to some physical representation. When we're thinking about language understanding in these contexts, we need to say something about a physical object, their properties, and so on. This is pretty conventional and pretty easy to understand. And our main argument is that these settings really transfer nicely to the computational social science settings, where in order to understand language, the kind of utterances that we see, for example, on social media that tend to be quite short, we need to know something about the speaker, what the targets that they're referring to, what else is going on in the world, such that such an interpretation can be constructed. As an extreme example, a phrase like "we demand justice" can really only be understood meaningfully in the context of some real-world event, right? So depending on who you are, we demand justice in the context of, let's say, the Russia-Ukraine war. It could mean get out of Ukraine, or it could mean, there is no Ukraine, if for example, you're Mr. Putin. We need to think about what are the challenges that come up when we're trying to operationalize such a framework. So, for example, what is the space of symbols that are relevant for characterizing such opinions? How can we obtain them and learn them? Can we ask humans to help us identify those symbols and guide learning, and through some form of interaction, building on the fact that these symbols are understandable to humans as opposed to purely neural representations? All right, so that was the talk in a slide. So now let's break it down a little bit more. So we're talking about opportunities for computational social science through neuro-symbolic NLP. And this is an especially good domain for applying neuro-symbolic learning. There is a lot of text coupled with a lot of real-world behavior that's easy to obtain. This is a very dynamic area where there's constantly things that happen, new opinions, new events. And just relying on traditional manually supervised learning, which has been tremendously successful for neural methods, can be quite challenging because, annotating data is expensive. And finally, from a more conceptual point of view, coming up with explanations for symbolic explanation for the kind of concepts that we're interested in is quite challenging. So we need to be able to reason about ideology, group interests, group identity, reasoning and arguments, and many more things that are quite challenging for NLP. To help motivate this, so let's think about a specific scenario. So if you're framing your opinions about healthcare as talking about a human right, then you probably voted in favor of Obamacare. So this is a way to tie together ideas from computational social science, such as framing theory, with stance prediction. I've written down at the bottom an example of how one would formulate this in a declarative framework. And in the second half of this talk, Maria will introduce a framework that we've developed for reasoning over such things. All right. Another interesting aspect of computational social science and in this context is the fact that in many cases we have access to the real world, and we actually need it to help disambiguate language. So there's been a lot of work on contextualized representations of language. A famous example here is the word sick, that could mean something good or something bad, but in some cases it could mean both. So if you see a statement such as "this movie is sick," it could either mean this movie is awesome, or it could also mean this movie has offending themes. And it could be really about the same movie, depending on who you ask. So really, we also want to consider symbolic representation that take into account the social context in which the text appears. Connecting that with the stance prediction problem that we saw, here's another example. So if the author is a Trump supporter, then the article is likely to oppose impeachment. In this case, we have a stance prediction. And we know something about the social network of the author. So if the author follows the One America network, then they're more likely to support Trump. So once again, we can take real world behavior, connect that to textual predictions. When it comes to exploiting such information, we can think about two ways to do it. The first one is through probabilistic inference. And in this case, we can come up with symbolic representations consisting of entities and relations and connecting them through probabilistic rules. For example, in this case, we have a user making a claim. That claim is using the safety frame. It talks about the topic as being related to safety. And as a result of that, we can now predict the author's perspective on the issue of gun control. Right? So sort of a way to tie things together. Note that talking about safety doesn't necessarily entail this, it's just highly correlated. So thinking about it in a probabilistic way is definitely needed. Another way to do this, to identify those kind of connection, can be done through the neural representation that's being learned. So we can think about joint social and linguistic embedding spaces in which we learn a representation jointly for social groups based on the kind of social relationships that they have, and for text based on the content that they produce. As a result of that, text that would have otherwise been more difficult to analyze, for example, because of the very dynamic nature of social networks, can easily be identified as having some kind of an ideological link, because we see it originates from well-established groups with well-established ideological backgrounds. So here's another extreme example from one of our papers. So a statement like, "we should keep our teachers safe," would be something that everybody would agree on, but would definitely disagree about the way to operationalize it. So it could either mean we should definitely ban all guns to avoid mass shootings, or it could mean let's give teachers guns so they can stop the shooters. And depending on where you stand, you would interpret that differently. As a general research challenge, we can think about finding ways to create context-dependent language representation such that the representation of the text and the social context would identify the meaning directly. Another way in which we can capture dependencies is through coming up with symbolic explanations. In this way, we can sort of think about it as parsing the space of opinions that we find on a certain topic. So more traditionally, we have the problem of stance detection. So we have a piece of text and we want to say where this text stands with respect to some policy issue. But we can think about abstract explanations for that stance by coming up with a set of symbols that would identify the underlying reason. So thinking about guns as a concept of safety tends to correlate with a pro-gun control perspectives, and it also provides an explanation for why we should have it. Other kinds of inferences that we want to make is about what kind of texts would have contrasting opinions, depending on the way they would formulate those kinds of explanations. So, and again, the main question that we have here is what should be the space of possible symbols and inferences that are needed for characterizing opinions. And in this case, we can borrow from the very rich literature on social science that have been studying these kinds of abstractions for a very long time. So I'm going in the rest of my part of this talk, I'll talk about a couple of frameworks that we have worked on, namely framing theory and moral foundation theory, and the kind of extensions that we've developed from them and lessons learned from them. Here's an example of how to tie together stance and framing. This is a text about the Obamacare or the Affordable Health Care Act. 6 years later, healthcare costs have skyrocketed and millions lost access to their doctors. So the stance is pretty easy to detect. Clearly, this is not someone who is in favor of Obamacare. But understanding that the underlying frame is economic tells us something about the reasons that they hold. So Obamacare should be repealed because it's too expensive. Can be succinctly represented by identifying that healthcare is framed as an economic issue rather than, let's say, a human right issue. Framing theory is a very well-established theory in communication. You can think about it as a lens through which a topic is perceived, organized, and communicated. And very often, this is used in an intentional way to bias the discussion towards a given stance, famously by politicians. So if you're talking about gun regulation as a question of safety or as of human rights, that clearly aligns with the kind of position that you're going to hold, and talking about it as a question of safety puts you in a better position to argue that some limitations are needed. From the NLP literature, there is a lot of work on identifying frames. There has been the more generalized policy frames that were developed by Boyce et al. Several years ago. They're applicable across all issues. So these are the framing dimension, the kind of frames that we identify in text are constant. Another line of work looks at domain-specific frames in which for every given topic, we develop a different set of frames, which could either emerge directly from data or developed by humans and then, go through a manual coding process. One of the big questions that we've asked is whether these kinds of generalized policy frames can act as good explanations. And this is from a work from 2 years ago. We've compared the generalized frames here on the left with the issue-specific frames that we have developed that emerge from data. What is sort of matrix this kind of graph represents is how often each one of those frames appeared in news articles aligned with the left or the right of the political map. Any points that's close to the diagonal means that it's pretty much used in the same way across both sides. And you could see that the picture on the graph on the left, many of those points are very close to the diagonal, indicating that they are not going to be very effective as explanations for the kind of opinions we're going to see in the news media. Developing these symbols through interaction with data resulted with a much stronger set of explanations. As you can see, that all of these points are much farther away from the diagonal line. Another way to think about another set of symbols that we can use to think about the underlying reasoning for holding opinions comes from moral foundation theory. Here are two tweets. Both of them talk about politicians' responses in the wake of a mass shooting event, and neither one of them explicitly mentions a stance on the issue of gun control. The first one, America woke up to heartbreaking news from Las Vegas. We stand united in our shock, our condolences, and our prayers. And the second one, another horrific shooting, another unspeakable horror. My thoughts are with everyone at the Marjorie Stoneman Douglas High School after this terrible day. Despite the fact that neither one mentions a direct opinion, we can sort of get what kind of position the author of each tweet would hold. And specifically, if we had to come up with explanations, we could say, well, phrases such as "we stand united," "our shock," "our condolences," uses a lot of "we" language, which sort of implies unity and avoids taking a direct stances. The other tweet uses a language that's a lot more visceral: horrific shooting, unspeakable horror, that shows a strong sense of, personal sense of disgust. Both of these are mapped nicely to moral foundation theory, which is a theory that was developed in social psychology by Jonathan Haidt and colleagues to explain human morality. And as they showed, and we've also studied, the use of moral foundations and the strength of the moral foundations correlate very strongly with different groups. They have identified 5 moral foundations, namely care, harm, fairness, cheating, loyalty and betrayal, authority and subversion, purity and degradation. And each one of them has both a positive and a negative aspect. So you praise people for providing care for those deserving of care, and people who cause harm get negative moral judgment. And then there's been quite a few works over the last few years looking at how to use, operationalize, and use these kinds of moral foundation in news media. One of the problems that we've had when using this as a set of explanation is the fact that while in some cases they work really well, in others, not so much. So as indeed Jonathan Haidt and many others have noted, liberals tend to emphasize fairness, conservatives tend to emphasize loyalty and authority. However, everybody cares. So the moral foundation of care is used universally by everyone. What we have noted is that while that is the case, people do not care or think that the same entities are deserving of care, and differences in social groups are indeed exemplified in this way. So you can, debug your common sense reasoning in this sort of political settings. If the target of care, meaning those deserving of care, are illegal immigrants, then the author is more likely to be a Democrat. If the causer of harm is illegal immigrants, then the author is a lot more likely to be a conservative. So you could clearly see how these kinds of attitudes align with political ideologies. We've developed a set of what we call morality frames, which are frame structures in which the moral foundation is used as a predicate, and it is associated with several different moral roles. We made a distinction between agents and target, those that are causing the harm or those who are the victims of harm, and positive and negative roles. So those who are being negatively affected are negative targets. Those who are providing care are positive agents. And we've associated that with each one of the different moral foundations. Interestingly, this provided us with a very strong vocabulary for understanding opinions. So this was done at an aggregate over political tweets from members of the House and the Senate, and we looked at several different topics. In this case, this example is about abortion rights, and these are the most prominent relationships that we've identified in their tweets. So we could see that in the figure on the left, Planned Parenthood is identified as a positive target for the Supreme Court. So the Supreme Court cares about Planned Parenthood. The GOP, the Republican Party, harms women. Title IX provides care for women, and so on. This is clearly from the liberal side of the map. Another set of explanations for the conservative side of the map is that the Supreme Court still cares about women. However, the GOP cares about life rather than harms women. Abortion clinics harm women and life, and so on. And we've noticed that despite the fact that for both political camps, care and harm were very widely used, by looking at the different roles, we were able to completely disambiguate the use of this frame. Okay, at this point, I'll stop and I'll let Maria talk about how we actually did it and some more technical details.
Can you see my screen?
Yep.
Yeah.
Okay, so I guess the next question is, how do we actually approach this challenge that Dan motivated about using sort of all this symbolic information and tie it to representations? And before getting into details of how to do this, I want to bring back some lessons from the past on statistical relational learning. So this idea of having this sort of high-level symbolic inferences is not new. And a lot of work has been done around this. And the key idea is that we can write this sort of first order formula that captures higher level patterns that are kind of like not necessarily entailment, but correlated. And we can add a weight to it that expresses the strength of that formula, or how likely it is to hold. Then we can think about problems as a set of pairs, formula to weight. And essentially, they describe an undirected graphical model that then ties all of these decisions together into a global decision problem. We can ground this in actual data then and use it for inference to try to evoke this sort of higher level patterns that we saw. And the go-to example in this type of frameworks, like Markov-logic networks and probabilistic sublogic, is this was when I have this sort of information with tied weights, like, well, if you smoke, you're likely to get cancer. And also if two people are friends and one of them smokes, it's likely that the other one also smokes. And we can see that these are tied to weights, so they're probabilistic facts. And the idea is to learn this from data. However, when we think about SRL in its initial form in these abstract settings and how to model this sort of computational social science NLP problems, things get a little difficult, right? Because our predicates map really abstract high-level information. So two approaches that have been approached in the literature in the past is to, well, then maybe try to enumerate relevant lexical and surface forms that evoke these types of concepts. This was something that was done by Johnson and collaborators, in which they looked at relevant unigrams, bigrams in data and try to tie those to higher level judgments like moral foundation and stance. An alternative form is to take advantage of really powerful classifiers, train them locally in like a standard way. So if you think about neural net, well, can we train a neural net based on some supervision that we have, and then use that to instantiate priors into our model, and then write this sort of weighted formula to reason about the different facts. However, we want to propose an alternative view in which we no longer do these tricks to try to initially learn a statistical model and then sort of plug it into the system, but try to actually take advantage of this both worlds about representation and inference. So we introduced DRail, which is a deep relational learning framework. It is declarative, so it's very similar in its form to MLNs and PSLs in that you have this sort of language of predicates, entities and rules that you can express expectations about the data, and they're associated to a weight. So from this point of view, it is essentially the same as previous SRL models in that we can use rules to express context, and it can be compiled into a graphical model. However, we want to expand these rules to have neural potential. So we want to take advantage of the fact that we can have this very expressive models that we can learn over data and replace this single weight that we used to have with a full neural net that then we can keep updating as we learn. And not only that, but we also want to take advantage of all the lessons that we have learned about representation and try to learn entity-specific and relation-specific encoders that we can reuse across different rules to learn these neural potentials. And you can think of this as some sort of multitask learning, or as we like to call it, relational multitask learning, in which we learn to shape the representation of entities that are repeated across different facts to try to learn a very expressive representation for them. And this is a very flexible framework because it allows us to define all types of relationships between facts and to actually use any type of information that we have available or any arbitrary feature representation to then learn a more expressive representation for them. So, from the symbolic part, this, as I said, is very similar to PSL. It's also very similar to some of the things Dan Roth talked about in the introduction of thinking about sort of linear problems or ILP as a framework for expressing constraints between decisions. And we augment this using a neural part, which is used to learn the weight that is defined over this sort of shared relational embedding space that we're talking about. So this describes essentially a structure prediction problem or a deep structure prediction problem in which we can plug in losses that have been studied in the literature for these types of problems like structure hinge loss or approximations to CRF loss and sort of learn this representation. But the key point is that we are not only learning to reweight those rules, but that we are backpropagating to this shared space of entities and relation, and we keep updating the embedding space. So we've broken down this problem into different components. We have specific embeddings for them. We plug in some symbolic inference that lets us derive structure loss, and then we keep updating this space. And the hope is that we learn richer representations about the relationships between these things, both at the inference level and at the representation level. So sort of a quick scenario here to sort of show you how this works in practice. So let's try to think about trying to understand debates. So we can think about debates as those are these platforms where someone posts a claim written in natural language, and then people come and post their views about it. Can think kind of like discussions on Facebook, let's say. So then our task is to try to identify whether the statement that someone's posting supports or doesn't support the debated claim. Then we have more information that we can use, right? So we have who the author is, and then we might have some external also interaction from people that come in and cast their support for either of the participants. And you can think of this as something akin to a like on Facebook. Apart from that, we might have some sparse information about these people and the things that they support that they've disclosed in this sort of structured debate platforms. So if we think about it, this results in several reasoning tasks. We have a textual inference task in which we are trying to identify the relation between post and claim. We have relations between authors and text, and we have relations between pairs of users. And clearly there's structure to be exploited. So we used Derail to express a problem like this. And then we looked at the impact of our modeling choices. Essentially, what we want to know is how much we can gain by using the explicit inference akin to an SRL model, and how much we can get by combining inference with representation. So to do this test, we reduce the amount of textual supervision that we have. So if we remember, we have all of these claims and posts, and we have the interactions between people. What happens if we only look at interactions between people and debate claims and reduce all of the information about posts? Then if we have a local model to predict this, obviously we can't do anything because we don't have any model to learn from, any data to learn from. However, if we try to exploit this social context at inference time, the way SRL models do, we can see that we can get some information from it. However, if we couple that that inference with also exploiting the representations through the embedding space, we get even better. And this is a trend that is maintained the more data we add. However, we have this effect that the impact is reduced. So this is very similar to some of the observations that Vivek talked about, that if we have a lot of data, our neural models can be very expressive, but when we don't have a lot of data, augmenting this with knowledge, in this case, in the form of external information or social information, can be very beneficial. So there are other examples of this learning paradigm that we introduced with Derail. And this is taking a step back from all the computational social science stuff and see how these ideas have been proposed by others in the literature. So ProbLog is a probabilistic logic framework. So it has a similar flavor to the SRL models in the sense that it relaxes logic rules to have probabilistic interpretations. And you usually can write it in this form. So you have a bunch of facts that have initial probabilities, and then you also have relations between them and expected outputs. The ProbLog was some work that tried to extend this framework to handle neural predicates in a way that is somewhat similar to what Derail did, in which some predicates could be symbolic and probabilistic in the traditional sense. So you have a statement, you have an associated probability with it, but others could really just be neural predicates. So in the sense that they receive some raw, messy input, and then they can be used to derive some probability. And some toy example that they use is if you have a word mathematical framework or a word computational framework, similar to the problems Sean was talking about. And then some of this information comes in the way of numbers written in a paper, then we can learn to predict which number we're talking about. So we have a neural predicate here in green, the inputs here in pink, and then the possible values here in blue. So I won't go a lot into details of how they do this, but it has a lot of similarities with our framework in the sense that inference is done in the same way you would do in ProbLog, in the probabilistic logic framework. But now they do a forward pass when they look at neural predicates and jointly learn parameters for both probabilistic facts and neural nets. But the loss is based on a single query output. So they sort of roll out the scenario, look at the output, and backpropagate it. Another framework that uses similar ideas is the probabilistic logic introduced by Wan and Poon in 2018. And in this case, what they wanted to argue is the case for neuro-symbolic representations as a way to deal with indirect supervision. So you can think about, if we want to learn a model, neural model to predict X given Y, but Y is unobserved, we might be able to source some weak labeling functions from additional data, weak data, external data, distance supervision. And then we can encode dependencies between the weak labels and the output to sort of learn the strength between this weak labeling function and the final output. And we also can encode constraints and instances or model expectations. So here is some example from their work in which they were looking at this information extraction problems from biomedical data. And they have different sources of indirect supervision, for example, relations in a knowledge base, some weak labeling functions using like data programming, and they can encode the relations between them using joint inference. So thinking about these ideas of indirect supervision, we wanted to extend this framework and think about human interaction as one way to think about indirect supervision. So as we've been motivated throughout this tutorial, humans are great reasoning machines. And they learned to match new data to previous acquired concepts. And this is a cute example of one of Dan's kids saying that his teacher said the lightning is dangerous and knives are also dangerous and they are sharp. So he can infer that lightning is also sharp. This gives us an idea that we can characterize learning problems using intermediate concepts that can be shared across many learning problems. And we can start to think about learning as a form of knowledge communication. So our working definition is that we can communicate human rationale about the task via intermediate judgments and explanations. For example, if we have this statement going back to our domain of interest, which is computational social science, we have a piece of opinion that says Since the vaccine, the number of patients that have come from miscarriages has quadrupled. A human can say, well, this is clearly an anti-vax statement because they're talking about harming pregnant women. So we can think about interaction or feedback over symbolic representations by sourcing knowledge about dependencies between concepts. So here are the open problems that we encounter as well. Where do these relevant concepts come from? How can we ground them in data? And how can symbolic representations be compiled into a classifier, which is something that we saw how to approach with derail. So now I'm gonna show a short example of how to put all of these different pieces together for the case of opinion analysis. So let's say that I have opinions about the COVID vaccine, and I have these two sort of paradigms. I have morality frame analysis, which Dan introduced, in which we are tying opinions to the sort of higher level moral foundations and breaking it down into who is the actor and who is the target that is exercising that moral judgment. And as he mentioned, this is a very sort of general cross-domain framework that doesn't just apply to COVID, it applies to any type of opinion. On the other side, we have very domain-specific problems like, well, what is the stance that someone's taking about the vaccine, and what is the reason that they're providing for this stance? In this case, they're talking about oppression, they're talking about the government or Biden being the actors of oppression, which is usually tied to a negative stance about the vaccine and to the idea of government mistrust. So I'm gonna go a little faster this because Dan already talked about it, but if we remember, morality frames capture differences in the actors and targets of moral sentiment, and they can help us explain opinions. So we can think about humans as a way to help us use the general concepts to identify domain-specific outputs. So if a human's looking at data that was initially clustered by some initial method and sees like, here the blue data has a lot of mentions about COVID being a hoax, being fake, and the red ones have a lot of mentions about the vaccines being dangerous and a health disaster. And they're trying to disambiguate the two. A human teacher could tell me, well, when I'm looking at the blue dots, I see a lot of cheating. I see authority figures being mentioned as the person doing the cheating, and the public as being the target. And this is likely an anti-vax and COVID fake statement. On the other hand, if I'm looking at harm and vaccine and as vaccine being harming and the public as being harmed, this is also anti-vax, but the reason is probably more that the vaccine is dangerous. And hopefully this can help us identify these opinions and disambiguate them. So this is a bit of work in progress, but we've done some small experiments in which we have this small session with NLP and computational social science researchers. They look at a lot of unlabeled data with some initial partitions, and then they are provided a main set of themes or reasons that people cite to refuse the vaccine. And we asked them to give us some higher level or identify higher level argumentative patterns that tie sort of this general information with this domain specific information and contribute just a handful of examples. Then we can compile this into this symbolic style framework in which we might have, an initial classifier that maps tweets and entities to stance, moral foundation, etc. And then we encode this high-level patterns into these dependency style rules. For example, if Fauci is harming, likely anti-vaccine. And then we can encode other type of contextualizing information like consistency between people holding the same stance. We can use the derail framework that I introduced before to work on this, which has these rules of this form when we're learning a weight. And then we've seen that actually doing this is beneficial to obtain better performance at actually predicting the general frames and also the domain-specific information. In fact, we see that the impact of inference has been very good, again, when we don't have a lot of direct supervision. We find that using this information makes our model competitive with just 25% of direct supervision, and that we can build fully supervised and base models that have no inference using just 50% of the direct supervision. And this is a recurring theme in this tutorial. Also, we can see the impact of humans providing these higher level judgments, even if it's just a handful. They help us generalize a lot of data, and we're able to improve predictions for the general themes using this type of information. So to summarize, we introduce deep relational learning as a general framework for combining symbolic and neural representations. The neural part captures implicit relations between entities in the embedding space. The symbolic part captures explicit interactions. And then the neuro-symbolic helps us make those consistencies propagated to the embedding space and kind of have the best of both worlds. This provides a convenient way to combine symbolic explanations into neural classifiers, which is really useful for these high-level complex problems, and it's amenable to human intervention. So thank you, and I think we're taking a break now.
So we meet, when do we start again?
In 10 minutes.
Okay, thanks.
Should we get started?
Sure.
Okay, so welcome back. So we're gonna just have a short discussion to close all of the topics that we've discussed here today. So first of all, thanks everyone for coming down. So one of the things that we've been discussing is this sort of tension between the neural and symbolic representations and their capabilities. So this has been a long-standing debate in AI more broadly, and this distinction is often characterized as, neural as being sort of system one, which has to do with thinking fast and perception on sort of raw inputs and stimuli. And then system two, it has to do with sitting down and thinking slow and reasoning, which is typically associated with symbolic reasoning. In our field, recently, there's been a large focus on perceptual tasks that are associated with this system one thinking, which has to do with consuming lots and lots of raw data, and as Vivek mentioned, assign categories to them. However, many real-world scenarios have challenges that are unique that drift a bit away from this way of thinking. A lot of times we need to understand relationship between higher level variables, and we saw different flavors of that throughout this tutorial. And there's a lot of considerations when deploying systems in the wild, in real scenarios, about fairness, accountability, and transparency, which becomes really difficult when we have this very large scale perceptual models. So not only in the broader field of AI, there's a lot of an ongoing debate in the NLP community. We just had in NACL 2022 a panel where people were discussing the place of linguistics and symbolic structures in the current state of NLP. And while we cannot deny the capabilities of large neural language models, their limitations are unclear. And this is just an example of me browsing my Twitter feed the other day, and right one below the other, we had a paper talking about how GPT-3 does not improve compositional abilities, and another tweet suggesting impressive demonstration of compositionality. So this is sort of the day-to-day of our field right now, in which we're trying to still understand what these models can and cannot do. However, it is more or less accepted that purely neural models face some challenges. For example, the energy efficiency. So large language models, training them and using them is prohibitive for most. Data efficiency as well. So we're talking about models that consume a lot of raw data. And a lot of times this has unintended consequences of just swallowing everything I can see on the internet and what is it that is being encoded in these large systems. And this is tied to the notion of explainability. So if we do not understand the models, how can we trust them in sort of real applications? And a bit of what we motivated towards the last section of the tutorial, human interaction. It's pretty in vogue right now in AI. We want to augment human capabilities with the ability to process large amounts of data. But how do we make use of the knowledge that we have in a way that is amenable to people? And another theme that was recurrent throughout this tutorial, which is the ability to reason beyond surface level patterns, and also evaluate whether we are able to do that and avoid having our models picking up spurious correlations. So these challenges turn into opportunities, particularly in the space of neuro-symbolic representations. And this is a phrase that most of these sections said at one point. Are they the best of both worlds? And how can we make them so? So neural methods, we know, are really good at training very expressive models. They can use massive amounts of raw data and identify patterns in them, and they're really good and successful. But symbolic models help us map these representations to symbols, reason over higher level patterns, and they have this nice property that they are inherently explainable and easier to manipulate. So a lot of this tutorial has been motivated by how to combine these two things. What is next for Neuro-Symbolic NLP? Hopefully throughout this tutorial, we did a good job of convincing you to care. But what is the next thing for this line of work? There are still a lot of problems to tackle. There's this broader question of what is the right neuro-symbolic representation. So neuro-symbolic can mean a lot of things. We saw a couple of different flavors of that throughout this tutorial. And the question is, well, is there one right representation? Are representations task specific? And how, can we design ones that are suited for the particular problems that we want to tackle? Another question is, what is the right level of abstraction? So what do we want to be able to use symbolic models to express, and what can be deferred to neural nets and what they can do well? There's a lot of questions and considerations around scaling and performance. So combinatorial inference is expensive, and it's one of the main reasons people are hesitant to do it. However, we find that backpropagation is also very expensive, and it has become prohibitively expensive the more we scale these models. And a lot of the work that we've done, we've found that our inference, even if combinatorial is no longer the bottleneck, sometimes just fine-tuning models can be difficult. So how can we find solutions in which can be more efficient, can be more data efficient, parameter efficient? And Yejin gave us some ideas around how to distill information into smaller models, make them more accurate. So there's definitely a lot to think about in that direction. And then finally, what is the role of symbols? So are symbols merely an interface for human AI interaction, or are they abstractions for the internal reasoning of neural nets? And what are the advantages of both? So I'd like to leave you with these big questions, and like this, there are many others. And I really want to thank everyone for being here. We can allow a couple minutes for any questions or comments that there are. We also have a little demo on how to use Derail to model one of these computational social science problems. If you still have the energy, stick around if you're interested. And yeah, thanks everyone for their attention. So I'm gonna leave just a couple seconds to see if anyone has any comments, and then we will move on to the demo. Okay, so I think I'll get started. If there's no questions or comments. Okay, so before I get started, I'll do a brief refreshment of the task that I'm going to use to demonstrate our framework. So Dan introduced this idea of analyzing political discourse. And one of the problems he introduced was this work on trying to look at tweets that were posted by US Congress members on a very highly debated and controversial topic, timely as well, as is the abortion debate. Our main sort of conceptual framework that we're bringing into battle here is morality frames. And we hopefully motivated morality frames as a way to analyze political discourse by breaking down statements into their moral foundations and the role different entities play in the overall moral judgment expressed. We are going to have in this domain a lot of opinions ranging from very on the conservative side, pro-life above all, there are no exceptions to the rule, to the most liberal point of view, which would be, the choice of women has to be upheld above everything. And then there's a lot of things in between. And we will look at the entities that are at the center of this debate. And these are things like women, babies' life, different US government institutions, and legislative bills. So I'm just gonna give a brief overview of the entities, and then I'll jump to the collab notebook. So here we're gonna decompose this problem into these entities and relations. We have this notion of an event. This, you can think about a time frame in which things are being discussed. In this case, we're gonna take all the tweets about abortion. So there's just one global instance of an event. We have the tweets that were written by the Congress members. We have the overall topic, which is abortion. We have ideology markers, so whether the Congress members belong to the Democratic side or the Republican Party. We have entity, both the notion of an entity mention and an entity group. So an entity mention can be something like the ACA, which refers overall to the Affordable Care Act. So we're going to group all mentions of the ACA into a single entity. We have moral foundations. Dan introduced them before. This is 5 high-level moral judgments, a sort of moral basis that account for a lot of our moral opinions. So these are things like fairness, care, purity, etc. And we have the sort of specific roles, right? Who is being the target, who is being the actor, and what polarity does it have? Is it positive or negative? And they have relations between all these things that sort of make our problem. So a tweet has an entity, a tweet has a topic, etc. So we're going to use Derail to analyze the abortion debate. So don't try to map this too much, but I just wanted to sort of give a high-level overview. So we have some base classifiers that try to map entities and tweets to roles and moral foundations. And then we have these constraints or soft constraints that express dependencies. So what's the dependency between the ideology and the moral foundation and role? And then a joint inference which says, the likelihood of a role and a moral foundation occurring together. So if we're talking about, babies, in which moral foundation we're likely to encounter it. So I'm gonna move to the collab, and please let me know if this is working. Can you see my collab notebook?
Yes.
Yeah, is it readable at all?
Yeah. Okay.
So this is available. I can share it with everyone, and you can run it on your own, on the web. I'm not gonna run it live to make sure it doesn't, take too much of the time while it sort of runs the inference, etc. But it's available for everyone. So to get started, we imported Derail here, which is our declarative framework that we proposed at the last part of the tutorial. And this framework is tied with this Python API to be able to interactively create neuro-symbolic problems. Our EMNLP demo paper is coming out soon about this. So this is what we do. So we have this notion of a learner, which is what is gonna sort of encompass all of our problem. And we support different types of inference algorithms, from exact inference to approximate inference. And we can use it to instantiate our problem. So we start by defining a learner, defining an approximate inference algorithm, and we build a parser. So instantiate a parser so that we are able to start to define our problem. So here we have the entities that I just defined on the slide. So I'm not gonna go over all of them again, but here they're listed. And then we can instantiate them in Derail pretty easily by just calling define entity. So then we have this notion of labels. So these labels correspond to values that predicted entities can take. For example, the universe of possible moral foundations and roles. And to be able to load these options, we use single column text files that identify the different classes. And then I tell Derail, this is the name of this label, this is the number of classes I expect, and here are the possible values. So once I have defined entities and labels, I can turn my attention to defining the predicates that express relationships between the two entities. So it's worth to note that we can have two types of predicates, actually three, but in this case, we want to talk about two. One of them is predicates that are observed. So we're going to have sort of instantiations in the data for them. And then we are predicates that are predicted, right? So we have supervision for them, but we're going to treat them as unobserved. And then we also can have latent predicates, which are predicates are going to be predicted, but that I don't have any supervision for. So you can define them in Derail easily by giving it a name, specifying which of the previous defined entities they're defined over, and then giving them a data file. The data file, if it's observed, will correspond to observed data. If it's predicted, will correspond to a supervision. And then if it's latent, I don't pass anything to it. Then Derail, as I mentioned, let us define arbitrary feature classes. So we can essentially use any type of information or that we have, and we can define these programmatically using Python. In this demo, since that's a little messy to show, we have taken care of this for you. But if you're interested, please take a look at our examples in our repository. And we can do the same for what we call scoring functions and neural nets. So scoring function can be broadly defined. It can either be a simple sort of computation, manual scoring function. I say, this score or this particular computation that is not necessarily neural, or it can be a full neural net written in PyTorch, and you have the flexibility to define them as you wish. And then we can instantiate them into Derail using both the scoring function class and the feature class. And then once we have that, in this case, we took care of them for you. We can turn our attention to writing down the rules that we care about to express these decisions. So as we talk about, we had both these sort of basic rules that essentially define classifiers. So these are the two ones that we have on top of here. So we have mapping an entity to a role, and we have mapping a tweet to a moral foundation. DREAL has this sort of syntax in which we tell it which is the relevant label that we define for this entity, and the question mark defines that it's unobserved and it needs to be learned. Then for each rule, we define an initial lambda, which you can give an initial prior for a weight, and then you define a scoring function that you define on your class before, which can be a neural net, and then a feature, a class, which can take any arbitrary feature. Then we can turn our attention to writing rules that capture dependencies between two decisions. So here we have dependencies between ideology and topic and moral foundation. And here they follow the same style. So even for rules that tie different concepts, we can also define features and we can define scoring functions. So this gives us a lot of flexibility as to what type of information to use to learn these dependencies. And then we can also define hard constraints. So sometimes we don't want to learn things from data. Sometimes we want to enforce it. So what this will do is give this sort of an infinite weight that will always have to hold true. So in this case, we're defining a hard constraint between role and moral foundation, because we partition roles into roles that are specific to moral foundations, like caring and cared for have to always be tied to care, the moral foundation. So we write this as a hard constraint. Then I can define the scope of my inference. So this essentially means which amount of data will be used together to construct the factor graph and the probabilistic graphical model. And I can do this by specifying an instance and an entity name. So in this case, I'm telling you everything that is in the same event has to be predicted together. And remember that we define event as everything. So in this case, everything is being predicted at the same time, but you have a flexibility as to how to define that. And then I can just say build models. I pass the database. I have the models instantiated, and then this builds everything for you in the background. So then I can actually subsample tweets and add them dynamically. So I can tell them which tweets to learn over and which tweets to test over. And then I can turn now my attention to grounding and inference. So given that this is online and we didn't want to do all the back propagation here, we loaded pre-trained models, and then this is just doing inference. So here we called a method called extract inferences that's going to instantiate the graphical model for us. And then by doing predict, this is going to run all of our model and perform all the predictions with all of the constraints. So in this demo, we didn't have any label data for these tweets. So these tweets were just tweets that we downloaded from people about abortion, but we don't really know what their moral foundation is. So to evaluate it, we looked at data analysis and visualizations to sort of explore the model. And the reason we did this was to make a case for this as an interactive process in which we can build on some sort of probing functions to take a look at how our data is looking and then refine the model on the go. So we created a custom module with few operations that you can use to visualize predictions. So it's going to plot the distribution of moral foundations per party, show you the most frequent entities in the data set, plot the polarity of role usage for a particular entity, and other things that we're going to kind of mess around with right now. So after all prediction is done, I tell, well, show me the most frequent entities that are being discussed in this data set. And as we see or expect, these are the sort of the entities that the discussions center about. So we have things like women, we have abortion, which is the topic, we have life, Wade, and Roe, which in this case is Roe v. Wade. We had a bit of issues with the pre-processing there. We have Trump, we have Planned Parenthood, reproductive rights, healthcare, and unborn. So then we can also take a look at the moral foundation usage by party. So we can observe, as Dan gave some intuition before of findings by previous social scientists, that Democrats are very likely to use the fairness moral foundation. And this is particularly true in the case of the abortion debate. And then for Republicans, we see a dominance in the case of loyalty and sanctity or purity, which is also a common finding. But similar to what we saw before, everybody cares, right? So in the case of care, we can see that there is quite a bit of competition between the two parties. So We can take a look at then role around a particular entity to try to get a feel of what's going on. So we take a very sort of a controversial entity here, like Planned Parenthood, and we look at the specific roles. So our intuition was that while moral foundations themselves might not be as indicative of the party, except for fairness, the entities would be. So if we plot the entity polarity graph for Planned Parenthood, we can see that the role of cost degradation is very high for on the conservative side, and the target of loyalty or betrayal, or actually providing care, is really high for Democrats. And these are expected things, but we can also see some errors that our model makes. For example, we have Planned Parenthood as doing cheating being somewhat liberal, which is not something that we would expect to find. So as to rephrase that, things generally look as expected, but we can spot some unexpected prediction. And one of them was that they do cheat for Planned Parenthood on the Democrat side. So we can further look into that. So do cheat has to do with fairness. So we can actually plot, oh, I think this didn't compile, but in sense we were gonna plot the entity graph, which is an entity graph that looks like that, in which we could see that Planned Parenthood was in fact looking wrong. And not only that, we also had abortion as having a weird sort of prediction there. So we have word knowledge, right, that we can try to encode into our model and let it learn from data. For example, we can say that given that we know that Democrats generally have a pro-choice stance, we can introduce a soft constraint that discourages a negative polarity for the abortion entity and let it sort of learn from data. So here we instantiate that rule. We say that in the case of abortion being mentioned, we don't expect that negative polarity to be found, and we add that to our model. And then by doing this, this actually affected our graph. So we used to have a wrong entity of abortion there that sadly I didn't seem to run in time to plot the thing, but it actually disappears from our graph. So this is sort of a way to interactively probe our model and on the go introduce more knowledge to sort of fix the high level patterns that we see. However, we can take a closer look by looking at specific instances that maybe weren't covered by our soft constraint, and we can inspect whether they're actually painting abortion in a negative light with respect to women, or if we are making some mistakes. So we have another function called show examples, in which we can actually look at examples of when this happens. So we are looking at entities in which the ideology is left, but the abortion is being portrayed as doing cheating on women. And we can see a couple of examples. So we can see that indeed in some of these cases, abortion should take a cheating. There are cases in which abortion shouldn't take a cheating role. What some tweets do have a negative tone, and they're all right. So one thing that we notice a lot is that they mostly talk about abortion as a constitutional right. And this wording is being wrongly picked up as a negative thing. So when we introduced derail, we saw that we have this like nice tension between the embedding space and the symbolic space. So we showed how to add a rule in the symbolic space to help clean up our results. But how about taking advantage of our embedding space to also bias results? So let's say I'm going to define a concept on the fly using natural language by just creating a really short description of what it is and let it be embedded in the embedding space. So I define abortion rights as abortion is a constitutional right. I define it as an entity, and I create it as a latent predicate that I have no supervision for. Then I can define a manual rule that tries to tie instances in the left to whether they mention abortion as a constitutional right. And then I define a constraint that says, if the person is in the left and they're talking about abortion as a constitutional right, then the entity can't be negative. And then by running this again, we can see that we reduce the number of errors that we have. So we are able to reduce the number of mistakes, and we can also inspect the tweets that are now associated to our new concept, just to see how good we are at grounding this concept on the fly. And then here are some examples that you can take a look on your own later. And then I left this as, a little game if someone wants to play with it. If you want to play with this for a different scenario, create another concept, create another rule, that is something you can play with. And I'm happy offline to answer any questions about Derail. And thanks again, everyone, for coming here. And I hope you enjoyed our tutorial.
Thanks, everyone. Thanks, Maria.
Thank you. We'll post the slides in the collab in the webpage.
Okay. Any final questions? No? Thanks. Bye.
Thank you.
Thank you.